Record. Okay. So units and scales. That's chapter 2. That's the first thing. Now, as I said, we use the metric system. So for length, what do we use in physics for length? Meters. We use the letter M for that. For mass, kilograms. And that's kg. And for time is always in what? Seconds. And electric current for current here. That's the first time you're hearing the word here probably, unless you took physics. We use ampere, which the symbol for that is A. And for temperature, anyone wants to take a crack at temperature, what we use?
Celsius.
Kelvin. And that's K. And amount of substance, the amount, how much? Chemistry, this is a chemistry question. Yep. Mole, which is abbreviation MOL. We lose an E there. And illumination, we use usually candles. How many candela, you know? For voltage, we use volts, but we'll get to that too. So voltages, we use volts. And that's V. But that's the basic units that we use. A lot of times you're dealing with large values and small values, so the number might be too big or too small. Well, they're not going to write, for example, if they said we have a charge, they said Coulomb for charges. For example, let's say we have a charge Q, we'll call it a charge here, of 0.00000000015 Coulomb. I think it's COL for Coulomb we use, I think. I don't know if it's, I think it's COL for Coulomb. The unit's in Coulomb, but I think it's COL for Coulomb, abbreviation for it. Now, they're not going to write a number like this. So they change that number to scientific notation. That number will be written as what? 1.5 times 10 to the power of what? -9. Now, engineers, we like to go by a power of 3, 6, 9, and so forth, and -3, -6, -9. So we'll start with the basic stuff. The basic stuff is 10 to the -3. What's 10 to the -3? That's milli. We use little m. 10 to the -6. That's micro. They don't use -4, -5 in engineering. It's always 10 to the -3, 10 to the -6, 10 to the -9. Micro, we use little mu there. 10 to the -9. That's a nano. Which is small n. All the small letters, that means is less than 1. 10 to the -12. Pico. Or pico, it depends who you talk to. P.
Capital P or lowercase p?
All P, all little, all these, the below 1 is always lowercase.
Okay.
10 to the -15. We don't deal with that in this class. Femto. and that's small f. 10 to the minus 18. Again, the last two I'm writing here, we don't deal with them. That's an atto, A-T-T-O, which is A. And it goes 10 to the minus 1 is zepto, 10 to the minus 24 is yocto, and we have other ones. But usually for us, this is what we deal with, especially when we start dealing with capacitors. We dealing with 10 to the minus 5, 10 to the minus 6. Inductors, the same thing, small values, 10 to the minus 12. Now, 10 to the power 3, positive 3. Anyone wants to take a crack at that? Kilo. Now, all of these will be capital letters. The ones more than 1 is capital letter, the positive power. 10 to the 6, which is what? Mega. Capital M. 10 to the 9th. Gigabyte, you know, talking about hard drive, storage there, G. Now you get the next one. 10 to the 12. Terabyte. That's a T. 10 to the 15. Again, wouldn't deal that much with that. Peta. And 10 to the 18. We have other ones. It's, or exa, capital E. Iota is 10 to the 24. Zeta is 10 to the 21st. What's Google? 10 to the 100. That's what Google is. You know. So, but you and I will be dealing with this, and you need to be able to convert from one to another, because when we have a problem, when we start doing circuits problem, they say we have a resistor. I don't even show you what a resistor looks like. We draw a resistor like this. We say the value is 5K ohm. So you have to know that K means what? 5,000. Or we have a capacitor. I don't show you what a capacitor looks like yet. And the value of that is 1.2 picofarad. Pico is what? 10 to the minus 12. So they don't put that in, but we have to know that. So that's why these units are important to us. They'll put them in, assuming you know what they are. Every one of these is a multiple of 3. Notice that's 10 to the minus 3, 10 to the minus 3 more than this, 10 to the minus 3 more than that, 10 to the minus 3 more than that. They change by 3. They call them engineering notation. On your calculator, if you look, there is scientific and there is engineering notation. So if you have some number that looks like this, they're not going to write this. You will not see that written in our book. 2.4 times 10 to the power of what? Negative 5? You won't see it. Why? Because they don't want to see a negative 5. They want to see a negative 3 and negative 6. So in our book, that will be what? 24 times 10 to what power? Negative 6, right? But what's a negative 6? Micro? So you'll see that written 24 micro. Everything has to be a multiple of 3. Okay. Coulomb, I guess C they use, our book. Just C without the C-O-L. Coulomb is C. Yeah. Now, if you take one electron, the electron has a charge, by the way, and you can find that in a physics or circuit book on the cover page. We usually have some constant values on the back side. This integration, calculus. Maybe not this book, but a physics book will have it. If you grab an old physics book, and I do have one here, I always leave one handy next to me in case I need something. There's an old physics book, probably from what year? Yeah, what do you know? This book has the tera, giga, mega, kilo, centi, milli, micro, nano, pico, right there. Can you see them? But if you look at this, is what is the mass of a charge of electron? Should be 1.6 times 10 to the minus 19, negative actually. Do we have that mass, speed, angle, energy, time, length, pressure? Maybe on the other backside. Huh? That's right there. Yep. On right here, we'll find it. Electron. Yep. 1.602177733 times 10 to the minus 19.
Want to take the whole thing, or do you want us to do?
Now usually we do 1.6 times 10 to the minus 19, you know. That's a charge of 1.602 times 10 to the minus 19. But that's what electron is. Now, electron is just a negative charge. You know, we have positive charges, negative charge, and we have neutral. The electron is one electron. It looks like this with the one negative charge in it. That's electron. And the charge of that one electron is 1.602 times 10 to the negative 19. A proton has one positive charge. This is a negative here. A proton has one positive charge. And how big that positive charge? Anyone? Yep, positive 1.602 times 10 to the negative 19. And neutron is what? It's a negative charge and a positive charge put together. Well, if you take this and add it to that, what's the charge to that? 0. C for Coulomb. So now, what's a current? So that's the next topic in our book. Charges, current, voltages. So if each electron is 1.602 times 10 to the minus 19, if I take a balloon and rub it on my body, you notice it sticks to you. What happened? There's charges. So let's say that balloon now has 1 million charges, 1 million electrons on it, because that's what happened when you rubbed it against your body. You freed a lot of electrons, and now they're stuck on the balloon. It's all over the balloon. 1 million of them. They go on the outside. Why they go on the outside? They'll be like all the way on the outside of the balloon. If you were on the inside of the balloon touching that, you wouldn't feel it. Why?
So they're in a static equilibrium.
Well, that's the farthest way they can get things
They push each other apart.
Yep, you're on the right track. Why they push each other apart?
They repel one another.
That's the answer. They're the same charge. What happens when we put the same charges next to each other? They don't like each other. They push away. So the farthest point possible now on the balloon is where? On the outside surface. So all these charges will be on the outside of the balloon. How much charge is on that balloon? Well, you're going to have 1 million, each one carrying that much charges. The Q now, the total charge for that balloon, is going to be 1 million. That's the number of electrons, times 1.602 times 10 to the negative 19 Coulomb. So the total charge is going to be 1.602 times 10 to the power of what? Negative, what's 19? Add to it or subtract from it 6, 13. So you have 1.602 times 10 to the minus 13. That's how we figure out what the charge is. Now, if this charge came from your body, from your sweater, you rubbed against your sweater, and that charge came from your sweater, what is the charge? This will be a negative here, right? So what is the charge on your body then?
Positive, the same.
Positive that number, because all these left your sweater. That means your body left now with equal positive charges there. So the charge on your body will be plus 1.602 times 10 to the minus 13 Coulomb. So everyone knows what a charge is? Oh, trying to fix the room and the computer there. Now let's look at currents. What's a current? If you take a plug and you plug into the socket there and you attach it to, I don't know, this light here, and you turn the light on, now there's current going through that. current really, if you can monitor that, if you look at the pipe or the wire like this, like a big pipe there, and somehow you can peel the top of the plastic on it and just watching it. This is just the pipe, and we just peel the top, the plastic on the wire, and we can count how many electrons are going through that. These electrons traveling through it. If you can count how many electrons, that's what the current is. How many electrons travel through that opening, that little cross section? If you can count them as they go by, that will tell us what the current is. So in our book here, it says the current is actually an ampere, is defined by counting the total charge that passes through a cross section of a wire during an interval of 1 second. Everyone see that? It's the number of charges the current here. So how many charges, how many electron pass through that little opening, this cross section? Like if you take a little skinny cross section, you can count how many electrons are going through it in 1 second. That's actually what the current is. And is measured in amperes, amps. That's a good definition, actually. I'll leave it better than that. I'll write it there. So mathematically, we're going to derive some calculus now here. Hopefully all of you took Calc 2. Current is defined as the change, the number of charges, the change in charges divided by time. So dq dt. That's what I is. So mathematically, the current I, it's the derivative So now let's think about this. This is a differential equation. Some of you have probably taken this semester differential equation. Differential equations, you have an equation that has a derivative in it. And the question, how do you solve it? Well, mathematically, I can multiply both sides of the equation by delta t, right? What will happen to this delta t now? Cancel. And you end up with what? dq equals I, I'm going to put the I first, times delta t, or dt. And to solve it for q, what do? How about we integrate both sides? What's the integral of dq? Just q. And that's the integral from negative infinity to t, I dt. Now, if you don't like to go from negative infinity to t, then you can break it down from negative infinity to 0 plus from 0 to t, I dt. So which you can write the integral from 0 to t, I dt, plus this will be what? Q at 0. The charge at 0. You don't have to start with 0. You can begin with t0. So if you really want to begin with t0, instead of 0, could be any value.
Quite see the bottom.
So instead of 0, I just decided to use t0. And the next, that's what the current is. So there's a relation between current and charges. That's the relationship. I equals dq dt. Or Q equals, you can use either one of these. Q equals the integral from 0 to t I dt plus Q0. If you don't like to use 0, from t0 to t I, this is I here, dt plus Q at t0. That's current. The next piece they talk about here is voltage. When you take a voltmeter, you plug it through the socket, it measures 110 volts. When you take a battery and say, what's the voltage on this battery? It says probably 1.5 volt. There's a battery here. Only have one. Okay, no big deal. I can take the battery out of my calculator. I'll take color them. Let's talk about a voltage. Voltage. Now, this is a battery here. You can see it's 1.5 volts if it's a good battery. The way we draw a voltage source, we go like this. The bigger one, that's really the plus, and this is the minus. So we draw that like that's a 1.5 volts. If I have two of them, I put them back to back, like this. That's equivalent to how many volts? If each one is 1.5. 3. Because what you have this one. It says here 1.5. And you also have another one of 1.5. Plus here, minus here. So if you combine them, this one is equal to one voltage source of 3 volts. Let's see if that's true. I got a digital multimeter here, cheap one. DC voltage, let's measure DC voltage, AC voltage, ohms. So I'm going to take this one, and this is labeled, see the plus on it here? Can you see it on the screen? Yep. So if I take this, now right now, this is really not attached anywhere. It says the voltage is 160.8. Can you see that little M? I don't know if you can see it. It means millivolt. So it's 0.16 volt. Should be 0, but you'll never get a 0. So now what will happen if I attach this one here? Oh, maybe just give me more wire here. Let me attach the plus side here to this one. And if my battery is good, it should read close to 1.5 volt. Might not be exactly 1.5. Hey, quiet. Don't move. I'll go like this. It's easier to hold it. That should read 1.5 volts. Ooh, that battery's not good. Notice, that's almost dead. Let's see if this one is bad too. Well, that's good. See this one? How big is this?
1.4.
1.4. Let me try this again. That is 1.4. So what's 1.4 and 1.4 if I put them together?
2.8.
Let's see if we get 2.8.
No.
Yep.
That was
2.8. What will happen if I reverse this? I'll talk about this in a minute. What are you going to see?
the same, but
0.
negative?
Nope, 0.
I just got 0.
1.4 times 10 to the minus 3. See the milli? If I reverse both of them, I should see minus 2.8. Or 2.9, whatever it is. If I put across my body, we have a voltage in our body. It's not a large voltage. It's leveling around what? Well, it's moving there. But a small value. We're talking about millivolt here. Doesn't even measure because it keeps going looking for it. It's like you're on a scale trying to find out what the number is. Around 46 millivolts, 0.046 volts, small value. Now let's see what happens when you take two batteries and put them in one direction. What does that mean? Now, when I draw a diagram like this, what that means, this end on the top, it's 1.5 volts higher than the bottom one. 1.5 higher than the bottom. So if I take my bottom one now and attach it, this is called ground. Ground is 0 voltage. This voltage on the top, if this is 1.5 volts, it says this end on the top should be 1.5 higher than that end. Well, this end is attached to ground. That's 0 voltage. So what is 1.5 higher than 0? This would be 1.5 volts. On the other hand, if I take the same voltage source, which is 1.5 volts, but instead of attaching this to ground here, I attach this to 5 volts. What's the voltage here?
6.5.
This one says this end is 1.5 higher than this. Well, this is attached to 5 volts, so that's why this is 6.5 volts. If I take the bottom now and I attach the bottom to negative 10 volts, and that's still 1.5 volts here. It says this end on the top should be what? 1.5 higher than this. That's what? Negative 8.5 volts. So just because you have 1.5, that doesn't mean it's 1.5 here. It depends what this end is attached to. If this is ground, you're right, that is 1.5. If this is 5, this is 6.5. If this is negative 10, that's negative 8.5. So when you take two batteries and you put them on top of each other like this, and this was my ground here, this is 1.5 and this is 1.5. Now according to this picture, it says this point here, the point right here, it should be what? It should be 1.5 higher than this end. That would make it what? 1.5. And according to the picture, this point here should be what? 1.5 higher than this one. What's 1.5 higher than 1.5? 3.0. When I reverse one of them, let's say this is 2 volts here. When I reverse this one, it says this end here should be what? If this is still 1.5, I can put any number there. It's on the first one, the direction is backward. That this end has to be 1.5 lower than this. So what is 1.5 lower than this? That makes this 1.5 volts. So on this point, it says this end has to be 1.5 higher than this. That will make it what? Back to 2 volts. So these two guys basically cancel each other out. That's why when you put a bulb in two batteries in a flashlight, you put them backward in the wrong direction, no lights will go on. Because you just cancel them out. It's like not having anything there. You put them back there, oh, now you got 3 volts. You ever seen the police officers, what they have for a flashlight? Seen how long it is? They put about 6, 7 batteries in it. Imagine the voltage in that one now. It's going to be a lot brighter. Plus, if you misbehave, they can clobber you on the head with it. You know?
No, that's illegal.
Well, that's as long as the camera's on. So that's what a voltage is. And the last piece is power. Power. The definition of power, it's voltage times current. Power can be positive, power can be negative. If the power is positive, that means that element actually absorbs power. If the power is negative, we use negative, that means what? Supplied. So how do you know if that element is supplying power or is absorbing power? Here's some pictures. Let me give you a picture. We have an element, we're not telling you what that is here. Not telling you what's in it, so you don't know. All I know, the voltage here, this end is plus, and this is minus, that's 2 volts. That means this end is higher than this by 2 volts. And I got 3 amps current going in.
What's the 2 in the middle stand for again?
2 volts. Now, is the power going to be positive or negative? Here we go. Ready for that? Power, it's V times I. Now, when the current arrow, the direction of the current, is directed into, going to the element of the plus marked terminal, we satisfy the passive sign convention. It says this convention should be studied carefully, understood, and memorized. In other words, it says that if the current, here we go, in other words, if, it says, if the current arrow and the voltage sign are placed such that the current enters the end of the element marked as a plus sign, the power is absorbed. So if the arrow, the sign of the current, let me read that while we're looking at this example. Let's look at our example. See my current entering which end of the voltage? The plus? Let me read that again, just in case you missed it. In other words, it says, if the current arrow, the direction, that's the arrow of the current, and the voltage polarity sign are placed such that the current enters, there's the current entering, see the current going in, enters the end of the element marked with the positive sign. Is this the end marked with a positive sign? Okay. Then the power is being absorbed, which means positive power. So in this case, the power for this is going to be positive 3 times 2, which is positive 6. Now, what are the units for power? Well, what's the unit for current? Ampere, which is amp. What's the unit for voltage? Volts, V. A times V. Well, they're not going to use A times V. They're going to use what? James Watts. James Watt actually did a lot of work on power and energy. And to give credit to him, we use W for power. And we use W for energy too. If you took the physics, probably you realize that. So the unit for power is always in watts or milliwatts. Now, let's try another example. I'll leave this one on the screen. My other example, here we go. An element. This is the minus, this is the plus, but wait a minute, this is negative 2 volts. And the current enters this way. That's negative 3 amps. Now let's think about this briefly here. This current is going through this, going to come out which end? That end. What about the other one now? We have a negative current. We have a negative voltage, if I saw that correctly. Yep, negative voltage. So how do we fix that negative voltage? Well, when you have a negative voltage, you can change the polarity. If you don't like that negative, flip these guys, make it plus, minus 2 volts. And there is the current entering this.
-6.
Well, I don't like that negative current. So notice what I did with the voltage first. Does everyone agree with the voltage here is fine? Because think about it mathematically. What does that mean? The minus the plus. It says this end is that much bigger than that end. Bigger. So this end, if this is 0, for example, this end is going to be negative 2 bigger than that. We'll add negative 2 to it. That'll be negative 2. What happens when I flip that? Now let's say this end now is 0. It says that end is going to be what? 2, according to this diagram, 2 higher than this one. That's a 2. So what's the difference between the plus and the minus? Between this and that. Isn't that 2 volts? What's the difference between this and that? Isn't that 2 volts higher than this? So it's the same thing. I just don't like the minus 3 amps going in. So if you have a negative 3 amps, how do we fix that?
Positive 3 amps going in the opposite direction.
Good. That means I got 3 amps going this direction. And if that 3 amps coming out of this direction, where was it going then? It was entering this direction. Because to come out of this, that means it was going through that.
It's exactly the same.
That's the same as the circuit above it, exactly. So what do we know about the power now? We have a positive current entering the That's absorbed. That's plus 3 times 2, 6 watts. It's the same circuit as this one. It just looks different. So if you're not a fan of negative, if you have a negative voltage, flip them, make it positive. If you have a negative current, change the direction of it, make it positive. Let me try another one. Now I got positive here, negative here. This is 4 volts. And I got negative 5 amps going in. Again, I don't like that negative current. Change it. That means I have 5 coming out. If that 5 coming out of this end, the plus end, it means it was entering what? The minus. So I can redraw that again. That current was going that direction of 5 amps. If you have a positive current entering the negative terminal, that's a negative power. Negative 4 times 5, which is negative 20 watts. Or sometimes we just write 20 watts supplied. The negative means supplied. Positive means taken, absorbed. So actually that was a source. That was a battery that supplied the power. When you attach actually this to a flashlight, the current travels through this, from the minus to the plus through the battery, because the battery has to supply the power. So you want the current to enter the minus terminal of that to make sure that battery is supplying the power. Everyone see that? Because if the battery has to take the power, who's going to supply power to the flashlight? So the battery has to supply the power to the flashlights. That means the current has to enter the minus end of it, positive current going through the minus end, through the source there, to supply the power for me. Okay, the last thing I think, well, not the last thing, a couple more things here, and just terminology. I've been drawing voltage sources like this, and that's fine, batteries. So we have different ways to draw them, and voltage sources and all that. So how do we draw what a voltage source looks like when we start looking at a circuit? How do we draw what a resistor is? Now, a voltage source. Let's talk about independent voltage source. If I said to you are independent of the class, what does that mean? Your test score is going to be independent of the class. What does that mean?
You don't put in the average?
Doesn't matter what the class does. Your score is going to be whatever you got there, and that's it. That class could have a 100 average. It doesn't affect your score. That class could all fail. It doesn't affect your class. It doesn't depend on anything else. So the way we draw an independent voltage source, we go like this. When you see a circle, that means independent voltage source. We always write the value, we go 5 volts. And that independent voltage source, when we draw it on a circuit like this, that means it doesn't matter when you plug it in, today, tomorrow, next year, next month, you will get plus 5 volts. Doesn't matter what you attach it to. You can attach it to an 18-wheeler. You can attach it to a little kitty, one of those remote control cars. You can attach it to a toaster. You're always getting 5 volts. Or I might have an independent voltage source like this of 7 volts. Or an independent voltage source, notice the direction is backward, of 4 volts. If you see one like this, you don't like the negative on the top, the positive on the bottom, what do? You can flip them. Or if you have a negative value, I don't like the negative. Flip that. So these two are equal. Yep. These two are equal, the last two, because of the minus sign. What's an independent current source? Again, the same thing, except we draw an arrow to indicate that's a current source, not a plus minus, like this is the direction the current is going. 5 amps. 7 amp. 4 amps. Negative 3 amps. If you don't like the negative 3 amp like this, that's equal to what? Change the direction of it and change that sign to positive. So when you start building circuits shortly, that's how we're going to draw a current source. That's how we're going to draw a voltage source when you see that. These are independent sources. They don't depend on anything. It doesn't matter where you plug them. It doesn't matter where you attach them. When you attach them, the value does not change. Now, dependent, voltage source. If I said to you, your grade is going to be, you missed the test, so guess what? Your grade is going to be 70% of dominant grade. Dominant gets an 80, so what do you get? 56. 70 times 80, 56, right? Dominant gets a 40. What's your grade? 28. 70% of his grade. So it's not a fixed value. Your grade is not going to be the average. It's going to be whatever 70% of his score. So if his score is good, you have a good score. If his score is bad, you got a bad score. So that's what a dependent source. The value of that is not a fixed number. The way we graph a dependent source, the way we draw it, we use parallelogram, like this. And we say the value of this 5 times something else, like the voltage cross, I don't know, some resistor, V1 or Vx. It's 5 times Vx. And Vx will be somewhere in the circuit labeled as Vx. So it'd be 5 times that number. This is a voltage controlled voltage source. Voltage controlled, because the voltage depends on a voltage. So this is voltage controlled. Dependent voltage source. Another one, it might look like this. Plus minus 0.2 times V1. That's also a voltage controlled voltage source. So both of these are voltage controlled. The voltage here depends on a voltage somewhere else. Sometimes your voltage, the value of that voltage, not the units, just the value of it, depends on the current. So I might say this voltage source, it's 3 times the current I sub x. And the value of this voltage source is going to be 0.2 times I1. These are known as current controlled. It's a voltage source that depends on the current. That's a voltage source that depends on the voltage. And the value of that depends what Vx or V1. So for example, I might look and see if I have a picture here. I'm jumping ahead like a few chapters later. Notice we have a circuit like this. I'm looking down the road. They label this voltage VA. Can you see it? And this is the source here, this voltage source, the value of that depends on this. It's 2 times that number. So whatever the value is. Or, I'll just take a block of this one here. It says the current, that's a current dependent source. The value of that current is 150 times VB. What's VB? Where is VB here? Or I sub B, I'm sorry, I sub B. That's I sub B. Where's I sub B? This current right there. Whatever the current going through that. So that's how we draw dependent sources. So dependent current source, almost done for today. We're just laying the foundation for circuit to start graphing them and solving them. A dependent source is always a diamond shape. So we go, for example, 3 times I sub x. Or it's going to go pointing down again, dependent like this. I sub 4 divided by 1,000. 1,000 of I sub 4. So these are current controlled dependent current sources. They depend on current. Or you can have a dependent current source that depends on the voltage. It's a current source, and the value of that 1/3 Vx. Or this current source of, we'll say, 1,000 times V1. That's voltage controlled. Is that our speaker? Voltage controlled current source, dependent current source. And the resistors we won't show you yet. Yep, but we'll talk about them next time. So right now, just to make sure you understand what a voltage source is, what a current source is, charges and current. Let's see if we have any homework assignment. Here's some homework. The first one, to make sure that you know the units. What is a micro? What is a milli? What's a nano? So converting from one to another. I'm going to snapshot these. Actually, you know what? I'll stop the video here.